Thank you. Bill Clifton was originally requested to give this talk, but he's busy putting together the last bits for the GRACE follow-on mission before it gets integrated on the spacecraft in Germany. So he asked me to talk about this. It's a very exciting time to be talking to this symposium. 5 years ago, I presented a similar talk on the LISA mission. And since then, a startling amount has happened from my perspective. There's been, that everybody knows of, the beautifully successful LIGO detection from last September. Also, coincidentally, right now, the LISA Pathfinder mission is making measurements to demonstrate perhaps the most risky technology on a space-based gravitational wave detector, LISA, which is the Gravitational Reference Sensor, the ultra-sensitive accelerometer. And we've been developing the real hardware for the GRACE follow-on laser instrument with an eye towards using very similar hardware on the LISA mission for laser interferometry. There is technically interferometry in space going on now in the sense of phase-sensitive microwave measurements on the GRACE mission, which has been flying since 2002. The GRAIL mission, which did the same type of measurement at the moon in 2012. The GRACE follow-on mission, which we're working on diligently to finish up, will also have a microwave instrument, but in addition it will have a laser instrument. So instead of 1 centimeter wavelength, 1 micron wavelength, it's inherently a factor of 10 to the 4 better sensitivity. The laser instrument is flying in tandem with the proven microwave instrument as a technology demonstrator for a planned all-optical version of GRACE. This is an Earth-observing mission, which sounds entirely different from LISA, but the remainder of this talk will be seeing the similarities and the way we can leverage technology from GRACE to LISA. LISA is now a European-led mission for scheduled launch in 2034. We're hoping that the developments with LIGO will allow us to accelerate the launch, perhaps 4 years. And NASA will have a contribution to LISA, perhaps the phase meter that we'll be talking about and other parts. So the type of metrology that LISA uses is heterodyne interferometry with lasers. It's based on measuring the beat note between 2 optical fields, so local laser and a weak signal from the distant spacecraft. It gives a radio frequency beat note. The signals are characterized as having a Fourier frequency in the millihertz band, very slow signals. So what that means is that on top of this megahertz beat note, there's going to be some small sidebands millihertz away. And they're very small. So the remainder of this talk will be discussing the GRACE and GRACE follow-on missions with relevance to LISA. I'll mention a bit about the LISA Pathfinder, what I know of it, and the near future for laser interferometry in space. The laser ranging instrument on GRACE follow-on, it can be characterized as its sensitivity, delta L. That's the precision with which the separation between the 2 spacecraft can be measured on the order of nanometers, and by the separation between the spacecraft itself, 200 kilometers. If you like, the ratio of those is the strain, and this number, you'll see a comparison when LISA comes up when I talk about strain. The concept for measuring Earth's gravity with a pair of satellites in the same orbit was described in a remarkably prescient paper by Milo Wolf in 1969. He talked about using lasers to do this metrology, not too many years after the invention of the laser. And we're finally catching up with Wolf, although the first GRACE mission from 2002 didn't have lasers, the next one will. And he described accurately, as we'll see on the next slide, how the Earth's potential affects the separation between a pair of satellites. So this is two satellites as they pass over a region of varying potential energy. The differential velocity between the satellites changes, and from that you can infer what the gravitational field is. So GRACE has been remarkably successful, flying since 2002. The lower right animated feature, if you look at the date indicator here, it's the Earth's geoid, if you like, over a period of several years, and the scale indicated by colors is centimeters equivalent of water. So this is how the Earth's gravity has been changing since 2002. I think this goes up to something like 2010. It gives a treasure trove of information for geophysicists, including things like the melting of the polar ice caps, underground water reservoirs. It's directly relevant to climate change. And its success was responsible for the approval of the follow-on mission, GRACE follow-on. This little animation shows the Earth passing under the satellite pair. That's one satellite, there's the other one. That wasn't very successful. Try it once more and then we'll give up. Okay. What happens, which you can't see in the animation, but at least you can see in this time domain trace, is there's the black trace is the relative separation. It's following the track of the satellites as they go over the Himalayas, say. First the separation decreases as the leading satellite is pulled away from the trailing satellite. Then the separation goes the other way as the satellites get closer, and you get this sort of pulse waveform from a point source. And this information is deconvolved to infer the geoid of the Earth. The satellites are in a polar orbit that precesses in a way that covers the entire globe in about a month. So every month a new geoid like this is measured, and that's what allows inference of the changes of things like the ice and water on the Earth. The GRACE follow-on mission with the laser is going to improve over the microwave sensitivity by perhaps a factor of 20. Launch date is scheduled for next year. It's to be a 5-year mission with the laser demonstrator part of it not required to last that long, but we fully expect that it will. The sensitivity is characterized by the spectral density of 90 nanometers per hertz requirement. And that is limited, fully expected to be limited by the frequency stability of the laser. So we put a lot of effort into stabilizing the laser with a cavity that we'll talk about. This diagram shows the principle of the measurement on GRACE follow-on. Incoming light from the distant spacecraft can be on the order of 1 picowatt. It interferes with a bit of local oscillator tapped off from the local laser on the order of 1 milliwatt. And the phase of that signal is detected by a quadrant detector in 4 quadrants. The sum of those quadrants, the piston phase, is what gives the ranging information. And differences between the quadrants is a way of measuring with high precision the alignment of the incoming light relative to the spacecraft alignment. The piston phase is used in 2 ways. It's either to measure the range at this spacecraft, the concept being the light is sent out, it's transponded with no phase change except a frequency offset. So all the information about the separation is contained back at the originating master spacecraft. Or the same hardware used at the other end by throwing the switch, the laser is stabilized to the reference cavity. These are the components that are being integrated on the spacecraft now. The laser, this specialized triple mirror assembly, which is a virtual corner cube. We'll see that, how that works on the spacecraft. The guts of the instrument is the phase measurement system and the laser ranging processor, the optical bench assembly that includes the fast steering mirror, the reference cavity here inside of its thermal enclosure, some more electronics. This is the cutaway of the spacecraft. It doesn't look much different from the original Grace 2 spacecraft, which didn't include the laser instrument, so we had to kind of nestle in the laser instrument in various spaces without much accommodation from the spacecraft. So you can see the laser instrument parts here, the electronics, the LRP, the laser itself, the small optical bench with the fast steering mirror, some electronics, and there's the cavity. A key part of Grace and Grace follow-on is an accelerometer, just as it's a key part of the LISA mission. This is necessary to measure the non-gravitational forces on the spacecraft. In both Grace follow-on, and LISA, that is a big contributor to that is radiation pressure fluctuations, which you don't want to be mistaken for the gravity or the gravitational wave signal. One of the requirements, the driving requirement on the laser is not so much frequency stability, but the ability to stabilize the frequency of the laser. That implies that the frequency actuators have to be adequate, but a key requirement is that the phase noise, frequency noise at high frequency is adequate, that the phase measurement system that we're talking about can track that phase without cycle slipping. And this laser does meet the requirements, and it's been under test successfully for several years now. So that's a somewhat modest requirement of 200 kilohertz per root hertz times this 1/f slope. The reference cavity, which was assembled by Ball Aerospace based on probably an original design from JILA, has excellent performance. Here's the thermal noise limit, so it's almost at the thermal noise limit, and it has a nice healthy margin against the 30 hertz per root hertz requirement. The performance at very low frequency is driven by temperature fluctuations, so a lot of the Ball effort was in thermal isolation. The laser ranging processor, as I mentioned, has the phase measurement system. It's probably an appropriate time to mention that the entire LRI instrument on Grace follow-on, the laser, the processor, the front-end electronics and photoreceivers and steering mirror all draw only about 40 watts. This differential wavefront sensing technique is used to provide what's in essence an active retroreflector to keep the outgoing beam aligned with the incoming beam with very high precision. To give you an idea of the scale, the beam divergence is on the order of 100 microradians. That will give a full cycle of phase difference between quadrants, so we can easily get nanoradian sensitivity of the misalignment from the system. It's fed back to a fast mirror with on the order of 100 hertz bandwidth, so any fluctuations in the spacecraft alignment are tracked out to keep the interferometer precisely aligned. I've already mentioned the triple mirror assembly, which is a virtual corner cube. It's necessary on Grace follow-on because the central real estate has already been occupied by the microwave instrument, but it also doesn't seem to be compromising performance at all, including thermal stability is very good. The beam divergence is shown here in a contour plot. An interesting point is that it's fairly clear and intuitive that the outgoing beam is limited by the telescope size, but the same telescope aperture limits the seeing angle for coherent detection of the receiving beam. So it's a symmetric arrangement, and a misalignment of the transmitter counts the same as a misalignment of the receiver. Because the uncertainties, at least initially, in the spacecraft alignment are much larger than the beam divergence, there's scanning needed for initial acquisition, in which the beams from both spacecraft are scanned. We have as fast as we can on one axis using this voice coil fast steering mirror at 100 hertz in the fast axis, and a slower optimized scan at the other spacecraft. Additionally, the bandwidth of the photo detection and the phase measurement is small compared to the uncertainty in the frequency, so we need to scan 5 degrees of freedom total, 2 spatial at each spacecraft plus a frequency scan. The frequency scan is the slowest, so this altogether takes 9 hours before we find the one set of those 5 degrees of freedom that gives a heterodyne signal. The saving grace is it only needs to be done once, we hope. Perhaps it can be done a few times during the course of the mission. There's a large cast of characters and companies that went into the GRACE follow-on laser ranging instrument, interferometer. And I think the part of the summary that I'm going to highlight is the connection between the LRI and what's to come, in combination with the LISA Pathfinder here called the LISA test package measurements. Many of the technologies for LISA have been checked off. The LTP is measuring right now as we speak the thrusters, the gravitational reference sensors, the main thing, the drag-free control, and the laser metrology. And there's not much I can say about Pathfinder results because I don't know them yet, other than the official statement is that it's working at or better than the requirement level. So that's very promising. That's the billion-dollar mission to retire one risk on LISA. This future all-optical version of GRACE that I mentioned will have better performance, primarily due to improved accelerometer, and that's made possible by having control of the spacecraft position, this drag-free control method, which GRACE follow-on doesn't have, but which Pathfinder does. So this is the LISA version of the strain equation that I presented before. Instead of nanometers of sensitivity, it's 10 picometers, and instead of hundreds of kilometers separation, 5 million kilometers, which is of course necessary to give a large gravitational wave signal, since the gravitational wave is characterized by its strain. This is a sketch of what the LISA configuration looks like. It's 3 satellites in a triangular configuration. The 5 million kilometers is these arm lengths. It's in an Earth-trailing orbit, and in operation, each of these links is actually 2 links. Each one is much like the GRACE follow-on laser configuration with outgoing and incoming lasers interfering. This is a quotation that I like from Michael Faraday from one of his lab notebooks. "Nothing is too wonderful to be true if it be consistent with the laws of nature." And I think that describes nicely the LIGO detection, which was for a pair of 30 solar mass black holes at a distance characterized by the redshift of 0.1, meaning it's not quite at cosmological distances. LISA, because of its much longer baseline, is sensitive to lower frequencies, which means much larger signals, much larger masses in the black hole pair, if that's what the signal is. 10 to the 6 solar masses, for example, it seems that every galaxy has one of these in its center, and galaxies colliding will give a signal that looks very much like the LIGO signal, except the frequency scale and the amplitude are somewhat different. And this is good out to the early universe cosmological distance of z equals 15. So to put LISA and LIGO on the same plot, the detection that made the news for LIGO was a pair of black holes coalescing out here around 100 hertz. Here's the similar curve for LISA. In fact, the signal that LIGO detected would have been seen by LISA in the early stages of its coalescence, several years before it was detected by LIGO, and then there would have been sort of a dark period when it passed up above the LISA band but was still below the LIGO band. There's also a whole host of interesting astrophysics that LISA is going to be sensitive to, including many white dwarf systems in our galaxy that can be resolved, some that can't be resolved, so it's sort of be a noise source of gravitational waves. And also small stars falling into black holes, extreme mass ratio in spirals. People have been thinking about these sources for decades, and it looks very promising. This is another sketch of the configuration. The orbit of the satellites as they move around the sun is such that the separation is not constant. It's changing by 10 to the 5 kilometers. So that presents a challenge to frequency stability, which we'll talk about next. Here's the telescope. Another noise source in LISA is angular fluctuations. They need to be controlled at the level of a nanoradian, yet another challenge. There are a lot of differences between the laser instrument, obviously, and LISA, but there are also a lot of similarities, including the detected power is going to be 100 picowatts roughly on both. The difference, of course, being that LIGO has much bigger separation, but it has much larger telescopes and more powerful laser. So this is why we think that, this is why we plan that the same instrumentation used for the phase detection on Grace follow-on can be carried over to LISA. The LISA measurement in simplest terms is a pair of measurements, local interferometry between the accelerometer, these suspended masses which are very free of anything except for gravitational forces at the level of 3 times 10 minus 15 meters per second squared per root hertz. So those distances are measured on the spacecraft relative to an optical bench, and that is combined with a measurement between the optical benches on the spacecraft. So when those are subtracted, we get the proof mass to proof mass measurement, which is what responds to gravitational waves, independent of the spacecraft motion. The LISA configuration has a total of 6 links, so there are 3 spacecraft here. Each of this pair is a link much like the Grace follow-on link, with phase measurements done locally between a strong local oscillator and a 10 picowatt-ish signal from the distant spacecraft. These phase measurements are combined on the ground to synthesize interferometer combinations in what's known as time delay interferometry, the purpose of which is to eliminate frequency noise. The frequency noise challenge is described on this slide. Of course, the measurements are all relative to the wavelength of the laser, and if the separation changes for a fixed wavelength, you'll see some number of cycles of phase change. But it's also true that if the separation doesn't change, but the wavelength changes, as indicated by the lengthening of this ruler, it will look like the separation changed. It'll be a noise source, and that sensitivity to frequency noise is described by this equation, that the fractional length change is equal to the fractional frequency change, and the fractional length change is exactly the gravitational wave signal. So if you were doing this in a laboratory, a way of eliminating the sensitivity to frequency noise would be to make a white light Michelson interferometer of equal arm lengths. Unfortunately, that's not an option for LISA. As I mentioned, because of the orbit, the arms will not stay equal. In particular, this quantity delta L, that was the variation in the arm length, that's even bigger than the number I was misremembering. It's 50,000 kilometers. And that's to be compared with the requirement of 10 to the minus 20 per root hertz of laser frequency stability, which is clearly orders of magnitude better than anything that's been achieved on the lab or in space or anywhere else. So how do we deal with that? And the answer is through this technique of synthesizing an equal arm white light interferometer by the way these separate phase measurements are combined, time delay interferometry. That's done in combination with the pre-stabilization on LISA will be much like on GRACE, using a reference cavity, somewhat relaxed requirements, maybe 300 hertz per hertz instead of 30 hertz per hertz. Plus another technique of using the most stable length reference available, which is this separation between the spacecraft itself in a bit of a bootstrapping method called arm locking. This says 2 or 3 of these will be needed. This one certainly will be needed, and we'll use either both of the others, pre-stabilization and arm locking, or just one. Either one would be adequate. So the arm locking concept is, it was considered controversial at first because it's using this, granted, very stable arm length to stabilize the laser, but because over this 5 million kilometer separation, there's a delay of 33 seconds, and people familiar with control systems will say, you can't do that, you can't have any loop gain at all with such a long delay in the loop. And for a long time, we didn't think more of it until it was noticed that, well, yes, it's true, there's a long delay for the round trip signal, but there's also a prompt signal. If the laser changes frequency a little bit, there's an immediate prompt signal, and there's also a delayed signal. So the control systems, there are implications for control systems, but the message is that it's not ruled out that modest bandwidth control loops can be used even with this ridiculously long delay for the arm locking technique. We looked in detail about using both arms and the shaping the control systems, the effect of the arm length changing, the knowledge with which we can measure that arm length, and the conclusion was that arm locking alone can provide adequate stabilization of the lasers such that this method of combining the signals on the ground won't compromise the performance compared to the requirement level, the 10 to the minus 20 per root hertz level. Another way of thinking of it is, in the simplest terms, the arm locking, the TDI, the time delay interferometry. Here's a synthesizing not even a Michelson, but just a single pair of spacecraft as the GRACE follow-on configuration. This is what you get if you have a real mirror here, that the phase as a function of time is the current phase minus the phase from before, because it just bounced back and had that delay in it. If you don't have a mirror here, but you only have local measurements, these are the two measurements that you get, and a little bit of algebra. This combination of those two measurements with this delay, L known, inserted, gives the same response as you get from a mirror. So this is this is the building block for time delay interferometry. It's bootstrapped into Michelson, and even not only in more sophisticated versions, not only takes out the effect of an arm length mismatch, but velocity effects as well, which can be important for LISA. Another limitation on LISA is The clock noise, the phase measurements are based on a USO, oven crystallized stabilized oscillator, which is too noisy by a factor of about 100. And the way that's dealt with is it's multiplied up from the phase measurement base frequency of on the order of 10 megahertz up to several gigahertz. And at both ends, so there's a gigahertz interference at both spacecraft. That can be used to measure what the clock noise is and subtract it on the ground. And that has been tested as well successfully. The combination of laser time delay interferometry, clock noise suppression has been tested on a test bed at JPL, and the net effect of that is that the required level of frequency noise suppression has been demonstrated here at the level of 10 to the 9, and we've also demonstrated other ancillary features of the interferometry, including ranging compared to the 1 meter required resolution using pseudorandom noise modulation. We've gotten 20 centimeters resolution, and another ancillary feature of LISA's optical comm using the laser links. That's been demonstrated on the test bed. So here's a long list of the elements of LISA. I'll finish here, I'll talk a little bit about the Pathfinder, the nice little optical bench. This is the key part that's being measured, the gravitational reference sensor. At the heart of it is a gold platinum cube of 6 centimeters length. The thrusters are very micronewton thrusters, high precision, low force to counter radiation pressure fluctuations. The laser on LISA Pathfinder is very similar to the laser made by the same company, TSAT in Germany. And there's the spacecraft before it was launched. It was launched. It's retiring the largest risk, which is the accelerometer sensitivity. And we're told that by the end of May, we'll hear the details and see what the actual noise performance. Very exciting to see this first key element of the LISA gravitational wave detector demonstrated. Still a number of things to do for LISA. One is the lasers that we're flying so far are low power. It's necessary to develop a laser amplifier, fiber amplifier that doesn't add noise. A detail of the orbit is these telescopes need to change their pointing by in the order of a degree, which is a challenge for all the other metrology, but there have been techniques designed for that at least, not tested yet. The thrusters that are on Pathfinder don't have enough fuel reserve for a full 5-year LISA mission, so they either need to be redesigned or some just larger fuel tanks added to them. So the status is that measurements are underway for LISA Pathfinder. In parallel, the laser ranging instrument with all the LISA technology on it is now being integrated on the spacecraft for launch in a year. And looking a bit to the future, 2030, we have the LISA launch. This is the final slide. Of the things that need to be done, drag-free accelerometers. It's been proven at a level of 10 to the minus 12 meters per square second per root hertz on the Goche mission from several years ago. And the requirement level for LISA Pathfinder is another 2 orders of magnitude. We're hoping we'll see 3 orders of magnitude better in a few weeks when the announcement comes. Interspacecraft laser interferometry has not been done, but we've tested it so thoroughly now that we're pretty confident that that's going to work in the 2017 launch. Thank you.